Right, so this is the part 2 of 1.1.1, where we're going to go through these three things here. I'm not going to read them out because you can see them. Let's just get on. So here we're going to look at the factors affecting the performance of the CPU, the clock speed, the number of cores, and the cache. So the clock speed essentially is just how many times the clock will tick, which will execute part of the fetch, decode, execute cycle. So if it's at 4.3 gigahertz, the processor, then it will do 4.3 billion fetch, decode, execute. Like that, or 4.3 billion times it will perform one of those per second. Okay? So fetch, decode, execute, fetch, decode, execute. So here is an example of clock speed. If I've put a task out, you can see that the little robot takes a little bit of time to fetch, decode, and execute the task. That's the speed it's doing. That's a slow clock speed. If I was to increase the clock speed, now you can see that it's doing it much faster. And that's an example of clock speed. Just how quickly can they do tasks, basically. More it can do per second. Now, the clock speed, what the clock is really just a pulse of signal high followed by signal low. So basically that means voltage and then no voltage or low voltage. And basically it synchronizes the components. So essentially it just goes on and then off and then on, then off. And you've got what's called the rising edge, which is actually where the thing normally does all its work. So on the rising edge, all the components will do their bit. The clock width is how long the clock holds half of the signal, really, the signal. And but the period is including the gap, so double the clock width, basically. And then the falling edge is kind of irrelevant. It just means it's stopping, but there you go. But what you need to know is that all the things happen early on in the rising edge. So here, about in this part here, is where all the stuff's going to do their bit. We finish by here, then down for a cycle of rest, etc. So that's the clock. Cores. A central processing unit can contain a collection of processors called cores, and each core is able to perform its own fetch, decode, execute cycle at the same time. So a dual core CPU, in theory, would be twice as fast as a single core, given the same attributes. But however, this is not necessarily the case, because if the software has not been written to take use of all the cores, and sometimes that's not possible, the game is very hard to use loads of cores because the cores work at the same time, and sometimes you need the information to have been completed before you can move on to the next task. Or if you're just not running enough programs at the same time, then it won't be as efficient. So more cores doesn't always double or treble the speed, but nearly always is quite a good advantage to them. But it does really depend on what you're running and how much software you're running. Right, now, what happens if we have multiple cores? Now, this is what happens. Let's say we have 4 cores. But let's say we've got loads of tasks. And look at that's going 4 times faster. There's no doubt about that. But lots of tasks are on. But what if I don't have a lot of tasks on and I've only got a few tasks? Now you might find some of the cores never get used. And even the ones that are being used every now and then, it's not an actual like extra, it's only a time saving of very little bit, as this one was nearly home. So unless you're losing lots of programs, or the program can make use of the cores, it's not always, say, 4 times faster or whatever to have 4 more cores than 1. So, parallel processing, okay? This is a program, like I said a second ago, and if that program can split the job up into multiple cores, then that's called parallel processing. But it's not always, because some, like I said, programs need to run sequentially and some don't. So I'm just going to very quickly... So here you can see a piece of software called Cinebench, and when I run it, you can see that what it's going to do, it's going to render the scene. It's like a 3D scene, and you can see here that it's doing more than one part of the scene at the same time. So this sort of rendering of a 3D virtual image is not a real world. This is being rendered. It's actually a 3D world, and you can see here that that was quite a good example of parallel processing, because obviously at that point you could see that we could use more than one core at a time to do a different part of the scene. So that's parallel processing. If you're ever encoding a video, like I will in a minute when I finish editing this, I will click render. And that's quite good for using multiple cores because it can have one frame be rendered by one core, another frame being rendered by a different core. So certain programs are better at parallel processing than the others. Right, so cache. Cache is a fast but expensive piece of storage inside or near the CPU that stores recently used data or instructions. In programs, there are often loops and other reasons which reuse instructions or data, and there's no need to refetch them from RAM if they're stored in cache. Cache is much faster than RAM, so if we can store it in cache, it will speed up the fetch part of the fetch, decode, execute. And I'm going to show you in a second example. Now, this is cache, and I'm going to have my fake system here with no cache, 1, 2, or 3 blocks of cache. So let's have 2. We've got 4 different tasks now. Assume there are 4 things we're fetching from. So because it's a green one, to fetch that from RAM. Now we look again, it's a blue one. We have to fetch that from RAM because we haven't got it in cache. Now it's a red one. Again, it's not in cache, so now we'll fetch it. And the red one. But now, instead of having to go to RAM, we don't need to go back to RAM. We can just instantly execute it because we've already fetched it and decoded it. This is significantly faster than going back to RAM because cache is inside the CPU itself and is significantly faster than RAM. And obviously having more cache just means it's far more likely that the task is inside cache. If you have a higher amount of cache, then more things will be in cache, and therefore it's more likely. Here we've got a 3 out of 4 chance because we've got all but the grey one in there, which there we go, we've got a grey one. Whereas if I only have one, then I will only have one in there, and this will obviously be far less likely, although we're lucky then, but not then. And then it's got to go to RAM more often. So having more cache is far more likely to speed it up. If you want my analogy, it's a bit like a chef. Imagine you've got your knife and your tools that you use the most right next to you. So that when you need to cut something, that knife that you use all the time is near you for ready for use. You don't put it back in the drawer or put it back in the cupboard, wherever you got it from. You keep all the recently and commonly used things near you so that you can reuse them quicker rather than to go and fetch them from the cupboards or whatever. Okay, so cache has different levels. Okay, level 1, 2, 3. There are sometimes more, but let's just talk about these. So level 1, which is usually quite small, 32 to 64 kilobytes. And each core inside the CPU, so if you've got a 4-core CPU, quad core, each one will have its own level 1 cache. Okay, and it's important to note that it's split into data and instructions, so they can be fetched at the same time in parallel. So I don't know if they split it directly in half. I don't know how it does that. That would depend on design, and each company could do it their own way. But the point is, let's say they do it in half. So let's say you've got 64 kilobytes of level 1 cache. You might have 32 for data and 32 for instructions. And yeah, and then depending whether it's a piece of data, like a number, it would get it for the number one. If it's an instruction, it gets it from the instruction one. The point of this is that you can fetch data and instructions at the same time, so it's faster. Okay, level 2, which is a large amount of cache, but is slower. Okay, it's normally around 256 to 512, but obviously this is just desktop CPUs. You know, big servers might have more. And each core has its own level 2 cache. So each core's got its own level 2 cache. So if there's 4 cores, there's 4 level 2 caches. For this one, the data and the instructions are shared. There is no splitting them. Okay, so that means that you can't get them at the same time. This is just probably a saving money thing. And level 3, which is your largest cache, is shared amongst all the cores. So it's not each individual core hasn't got this cache. It's all the cores share the same one. And that's usually much bigger, obviously, because it's shared across all the cores. As I've said there, these are for standard desktop CPUs in 2022. The actual size of the cache varies with design, cost, and use case. Obviously, if you've got a different computer, cheaper one, or a bigger system. And it could be a processor that does something else. It might not be a desktop CPU. So, now, as I said in the video, having more cache would increase the chance of finding an instruction there before having to go to main memory, so thus speeding up. So if we have a quick look at a picture of it, this is not to scale, by the way. The level 1 and level 2 cache are in each core, much smaller, but they're faster. As you go down the list, it goes slower but bigger. Okay, so main memory slowest but biggest, level 3, second slowest but big, faster but small, fastest but very small. And then level 3 is shared amongst all the cores. So if you had 8 processors inside the CPU, 8 cores, then you would have, this would be shared amongst 8. Right, so look at pipelining now. Pipelining is a technique that allows a processor to improve efficiency by overlapping the fetch, decode, execute cycle. So here's my Mario pipe. It's obviously not how it looks, but here's the point. Let's say F is fetch, D is decode, E is execute. So let's do the fetch. So we're fetching instruction 1. So the pipeline fetches instruction 1. Okay. Then the next step would be decoding it. But while we're decoding instruction 1, somewhere else, possibly another core, we're fetching instruction 2. Okay, so we're overlapping the fetch, decode, execute. Then, when we go on to the next stage of the slot cycle, we're executing instruction 1, whilst we decode instruction 2, and then another place is fetching instruction 3. So we're sort of, rather than doing fetch, decode, execute one after the other, we're overlapping them so that we're always doing, one of the things at the same time. This is called pipelining and is quite good to improve efficiency. Now, there is a slight problem here. I'm just going to drop out of that because I need to highlight this. Let's take this program. Now, these aren't individual instructions, but let's pretend they are. Right, so let's take this for example. I'm going to have the colours being fetch is green, decode is blue, and execute is pink. So, firstly, we could be fetching this. Click. Then, we start to decode it, and we begin to fetch this. Okay? Red. There we go. So we're decoding this and we're fetching this. Right, next stage. We're executing this. We're decoding this. And we're fetching this. This all makes sense so far. Brilliant. Okay, now we've executed that now. So now we're executing this. Decoding this. And we're fetching this. And you can start to see the problem. When we execute this, we're going to figure out that actually we're not going to do those 2 lines of code because age is not greater than or equal to 18. So if a program has a lot of branching out, if, switch, or case, or whatever, it may not benefit as much as others because it'll be fetching and decoding in a buffer, so it's not causing any performance loss, but it's not getting a performance gain of pipelining. So that can be one issue with pipelining. Still, you generally get a benefit, but not as much with certain types of programs as others. Because we're not going to execute that. And now actually we need to fetch this. So so next execute cycle, we're going to be fetching that. And we've lost all of any benefit of any pipelining. And we're back to square one. Right, that's pipeline. So von Neumann, Harvard, and contemporary processor architecture. Originally, computers were only running one program and that could not change. Then came the idea of something called a stored program, which allows computers to load a program and execute a new program, and that program could change every time you want to load a new one. Okay, instructions can be loaded into main memory for execution, and they're fetched, decoded, executed one at a time in a sequence. Okay, so you load the program into memory, fetch, decode, execute. Now, there are 2 main current modern architectures, the von Neumann and the Harvard architecture, and I'll go through them. In the Harvard architecture, data and instructions are stored in different pieces of memory. Okay, so let's go to here. So imagine you've got a memory, you've got 2 sections of memory. It's probably the same block, but 2 sections. It's been sectioned off. One is for data and one is for instructions. So data could just be numbers, all in binary, of course, but I'm just writing them in decimal. Okay, and this could be instructions. Add, jump, shift, load. These are obviously given in a mnemonic. They're still being a machine code. So basically, they have a different bus, one for the data, one for the instructions. So that data they will send the information to the CPU in different places, and this allows for faster access because you can do what's called parallel access. Say you want to access this and this, you can access them at the same time because add can shoot down this wire, 56 can shoot down this set of wires, and there you go. Harvard architecture is usually used in time-sensitive stuff, so things like in hospitals or digital signal processing, which is where you look at waves on a machine and things like that, like you analyze sound waves or other things that analyze signals because they need to be very fast. The very fast machines or quite simple machines which use the Harvard architecture, like embedded systems. The only downside to this architecture, really, apart from cost, a bit more expensive to have 2 buses, is that what happens if I'm like here, I've ran out of space in my data, but I've got space in my instructions. I want to put some more data in, but I'm basically this memory can't be used for anything but instructions, so it's just sitting there. So it's kind of annoying because you've pre-allocated what you're going to have for each one. So you don't, it's not as easy as you haven't got just 2 gig. You might only have 1 gig each side, and that might be a problem because you're not quite sure how much you need for each half. So the von Neumann is basically different in that everything is stored together. So these would be stored all in one place, and it would be like this. You would have one instruction, jump, load, whatever you're going to be. All the data would be with the instruction here. But of course, the benefit, as I said, is if any free space can be used for data or an instruction, and it's fine. Obviously, though, there's only one bus, so data that would have to take longer to be sent down the line because add and 56 are going down the same wires. But of course, it's cheaper and easier to design a system with just one bus. So there is the benefit of that. If we go back here and we compare them, I'm not going to talk over them because you can just read them and pause them at your leisure. But yeah, that's basically the system. And there you go. Now, contemporary design sometimes mixes both those sort of ideas. So, for example, main memory in a modern computer uses the von Neumann style, as we just discussed. Okay, that's what we're talking about. It's about main memory. But on level 1 cache, if you remember before, level 1 cache is actually split up just like the Harvard style. So a level 1 cache on a computer is actually like this. Exactly the same as the memory in Harvard. So there is a little bit of a mix of both. So level 1 cache obviously splits it to speed up parallel instruction and data retrieval. But yeah, so there's a little bit of a mixture of both, although it is mostly the von Neumann architecture. The system is mostly made up of that. Okay, there you go. Thanks.